let's proceed with example number 3. So this time around, so we move from the population problem. So we'll be talking about money this time. So a slow economy caused a company's annual revenues to drop from 530,000 in 2008 to 386,000 in 2010. If the revenue is following an exponential pattern of decline, so what is the expected revenue in 2012? So to resolve this problem again, so this time around, since this is no longer a population, so I'll be using a new variable. So we're talking about revenue. So I'll be using R. So R would be the revenue at any instant of time. At any time. And then initially, the annual revenue so dropped from 530,000 in 2008. So if we are considering 2008 as our reference time, instead of using 2008, so we'll be using 0 for that, so that it will not complicate our solution. So my time 0 here, okay, so my time 0 is actually equal to 2008, or my time of 0 is equals to 2008. So in short, the revenue when time is 0 is equal to 530,000. And then there is a decline. Okay, so from 2008 to 2010, so that is after 2 years. So after 2 years, the revenue, so from 530,000, so it became 386,000. So I do not know what's happening with the economy or with the company, but probably it's because of the probably a recession or a slow economy. That is why there is a decrease on the revenue of the given company. So from the given problem, so if the pattern continues, okay, and then the pattern is an exponential pattern, so that is our context clue that the formula that we will be using is still the same. So what is the expected revenue in 2012? So for our required, so what do we expect? So in 2012, so that is 2012 is 4 years after 2008. So therefore, so we are to find what is the revenue after 4 years. So for our solution, so we will be using the same solution. So but instead of P, so this time, so we will be using R to be equivalent to C e raised to KT. Okay, so since the given problem mentioned that the decline on the revenue so follows the exponential pattern decline. So that's why we will be using the same formula. So again, so just like with the previous examples, so we will start when time is equals to 0. So that is when T is equals to 0. So R is 530,000. So 530,000 is equals to CEK times 0. And that is equivalent to 1. So therefore, C is equals to 530,000. So substitute it. So we'll have R is equals to 530,000. Then EKT. And from our second given, so we have that when time is 2, so R declines to 386,000. And from here, so we could use our equation. So R is 386,000 is equals to 530,000. Then E, our time is 2, so that would be 2K. And from here, so we could have the 386, so divide it with 530. So that is approximately 193 all over 265. That is equals to e raised to 2k. And then taking the logarithm of both sides, so ln 193 over 265 is equals to ln e 2k. So giving us the ln 193 over 265 to be equivalent to 2k. And thus k is equals to ln of 193 over 265 all over 2. So that would be our k. So giving us our final equation to be r is equals to 530,000 e raised to t, then ln of 193 over 265 all over 2. And finally, so we could determine the decline. Okay, so the decline on our amount or the revenue. So after 4 years, so we are expecting that the revenue would be less than 386,000. So that is when time is equals to 4. So what is our revenue? So R then would be 530,000 e raised to, so we'll have 4 ln of 193 over 265 all over 2. Or that is simply 4 divides 2, that is 2. 2 ln of 193 over 265. Then taking the exponential function of that and then multiply it with 530,000, and that will yield to 281,124.53. And that is our expected revenue. So after 4 years, if there is no change on the economy, okay, if there is still a recession on the economy, so we are expecting that after 4 years, so the revenue will decrease to $281,124.53. Okay, so that is our example number 3. So let's have another example. So for example number 4, this one is an age problem. So we will be determining, so when did the plant die? Okay, so using some carbon dating formula that we have. So for this particular problem, so we have carbon-14 is a common form of carbon, so which decays over time. And then the initial amount of carbon-14, so contained in a preserved plant, is 10 micrograms. So when it was found out, so there are 10 micrograms of carbon-14 initially. And then if there is currently 1 microgram of carbon-14 remaining in the preserved plant, so after some years, so the 10 micrograms, so which was found initially on the plant, okay, so it decays to an amount, so which is equivalent to 1 gram. So this time around, so we are to determine, so approximately, so when did the plant die? So in short, we are just going to determine so the number of years. Okay, so since the plant dies, so we are just going to determine what is t. Okay, so what is t? So when the amount is equivalent to 1. Okay, so to resolve such problem, so we will be using or we'll be determining the given. So since this is an age problem, okay, let me just use A. Okay, so A would be equal to the amount of carbon-14. So amount of C14, carbon-14 at any time. And then it says here that the initial amount of carbon-14 that was contained, so when time is 0, so there are 10 micrograms. So 10 micrograms of carbon-14 that is present. So micrograms. And then if there is currently 1 microgram, okay, so after a certain period of time, okay, so which we do not know. So there is only 1 microgram that is present. Okay, so only 1 microgram that is present. So we are to determine what would be that time. Okay, so approximately when did the plant die. So for our required, so actually that is what is required. So what is the time? Okay, when that is 1 microgram. Okay, so what is the given time? So for our solution, so since again there are no amount or there are no relation that can be seen on the given problem, so we are assuming that this is an exponential decay as well. So since the relation is not specifically mentioned, so this is an exponential decay as well. So we'll be using the same formula. So that is A is equals to CE But what we can see here, if you could notice on the previous examples that we have, so there are always two given. Okay, so the initial and then another given. However, on this particular problem, so there is only one given, and that is the initial value. That is 10 micrograms of carbon-14 that is present initially. But other than that, there is no other given. But whenever we are talking, okay, so whenever we are talking about the carbon-14, the half-life of the carbon-14 is known, or in short, that is constant. It does not change. That whenever we are referring to the half-life, okay, so after a certain period of time, okay, so after a certain period of time, or that is approximately 5,730 years. So after 5,730 years, so the amount of the substance decays at 50% of the original amount. So in this case, that is after 5,730 years. So that is after 5,730 years. So approximately, the original amount decays, so by 50%. That is 0.5 times 10, so giving us the 5 microgram. So this particular relation so will give us the second given needed in solving such problem. So always take note of that whenever there is an age problem that involves a carbon-14, so the typical half-life that we are using, so for the carbon-14 would be 5,730 years. So once we have this one, so we could resolve it using the same steps that we are using before. That is when time is equals to 0, our amount of the carbon-14 is equals to 10. So again, so A is 10, is equals to C EK times 0. So that would be 1. So therefore C is equals to 10. So yielding to our new equation to be A is equals to 10 E KT. And then based from the half-life of the carbon-14, that is when T is equals to 5,730, the amount so changes to 50% of the original value, and that would be equal to 5. So therefore, we'll have 5 for A, and then 10 EK time is 5,730. Then 5 over 10 is 1 half. So we'll have 1 half is equals to EK 5730. So taking the logarithm of both sides, so ln of 1 half is equals to ln of EK 5730. So giving us ln of 1 half is equals to 5730K. And K then would be equivalent to ln of 1 half all over 5730. So now that we have that, so we could substitute it on our original equation, and that is A is equals to 10 E, and then that would be T ln of 1 half all over 5730. Now that we have our final equation, so we'll be able to determine the time. That is, what is the time? So when the amount of the carbon-14, when the plant was found, so what was remained is only 1 microgram. So that would give us 1 is equals to 10 e raised to t ln of 1 half all over 5730. So 1 over 10 would be equal to e t ln of 1 half all over 5730. And taking the logarithm of both sides, so ln of 1 over 10 is equals to ln of e t ln of 1 half all over 5730. So ln of 1 all over 10 is equals to t ln of 1 half all over 5730. So finally, t then would be equal to 5730 ln of 1 all over 10 all over ln of 1 half. So what would be that time? That would be 5730, then ln of 1 over 10 divided with ln of 1 half. And that will give us to have a 19,034.65 years. So that is how old that plant would be. That is 19,034.65. So that's old. It's even older than Christ. So that is 19,034.65 years. Okay? So that is our example number 4. So let's proceed with our example number 5. So if we have the same or similar example, so this one is a population problem again. Okay, so we did go back to a population problem, but the question is different this time. So suppose a population of insects grows exponentially. So that's the context clue. So we'll be using the same formula. There were 130 insects after the 3rd day of the experiment, and then 380 insects after the 7th day. So approximately how many insects were in the original population? So there's an experiment about the certain insect. So So how will the population increase? So during the initial stage, so we do not know how many are there, but after 3 days are 130, and then after a 7th day there are 380. So in short, we want to determine during the start, so how many insects are there actually there. So let's have our given. So since this is a population, so we'll be using P again. So that is the population of insects at any time. And then there were 130 insects after the 3rd day. So P of 3, that would be 130. And then P of 380, so that will be, P of 7. So P of 7, so after 7 days, so there are 380. So originally, how many insects are there initially? So we're expecting that should be less than 130. So for our required, so of course, so we are to determine what is so what would be the population, so when time is equals to 0. So for our solution, again, so we'll be using the same formula, that is P is equals to CEKT. And then, so let's use our initial condition that when T is equals to 3, P is 130. So P is 130 is equals to C, E, K, then time is 3. Okay, so 130 is equals to CE 3K. And then we will be utilizing the second given. So when time is equals to 7, P is 380. So 380 is equals to CEK times 7. So giving us 380 is equals to CE 7K. From here, so we could equate. Okay, so for us to get the value of K, so if I'm going to get the value of C here, so this will result to C to be equivalent to 130 all over E3K. And then this one, so C is equals to 380 over E7K. So equating both C, so since those are, that's an arbitrary constant which is the same, so we could have 130 over E3K is equals to 380 all over E7K. So cross multiplying E7K all over E3K would be equal to 380 all over 130. So E7K over E3K, that is the same as E4K. And then 380 divided with 130, so we have 38 over 13. So getting the value of K, so that would take the logarithm of both sides. So ln e raised to 4k is equals to ln of 38 over 13. So from there, so 4k would be equal to ln of 38 over 13. And therefore, k is equals to ln of 38 over 13 divide it with 4. So now that we have K, so we can compute for C. So C, let's say I'm going to use our first equation, that is 130 over E3K. 130 over E3K. Or that is 130 all over E3, our K is ln of 38 over 13 all over 4. Right, so that would be our C, and we have our K. So now that we have the C as well as the K, so we can now compute for T. Right? Or what would be P when K is 0. Actually, what we need here, we have P is equals to CEKT. So since T will be 0, okay, so when T is equals to 0, so what is P? So P then would be equal to C, so which is 130 all over e raised to 3 ln of 38 over 13 divided with 4. So that is our C. And then E, our K is ln of 38 over 13 divided with 4. And then our time is 0. So in short, so this would be e raised to 0. That would still be 1. So our population then initially, so would just be this formula. That is 130 divided with shift E and raised to 3 ln of 38 over 13 and divide it with 4. Okay, 3 ln divided with 4. So that will yield to 58 point. So actually that would be 58.15. But since there's no 0.15 insect, so we will round it down. So P then is approximately equal to 58 insects originally. Okay, so that would be the number of insects initially. So after 3 days, so the 58 becomes 130, and then after 7 days it becomes 380. But originally there are only 58 insects. So let's have our last example. So for the growth and decay, and this time around, so we have a swimming pool, and it drains at the rate proportional to the square root of the volume remaining. The pool initially held 375 kilos of water, or is that kilos? Or kiloliter, sorry. 375 kiloliter of water and drained 75 kiloliter in 1 hour. So how much water would be remaining in the pool after 4 hours? So this is a rate problem. However, the relation or the rate of change on the volume of the water is given. So for our given problem, so let's say we will be using, so that would be water. So I'll be using V. So that would be the volume of water in the pool. Of water in the pool at any time. So that's the volume of the water that remains in the pool at any given time. And then the pool initially held 375 kiloliters of water. So initially, so when time is 0, so the volume is 375 kiloliter. And then drained 75 kilos in 1 hour. So after 1 hour, so 75 kilos was removed or drained out from the pool. So therefore, how much of water remains? So remember that our V is the volume of water that remains in the pool at any time. So we are talking about of the amount of water that is present. Okay? So what is available, not water that is taken out from the pool. So therefore, the volume of the water after 1 hour, so that is 375 minus 75. So what remains would be 300 kiloliter. So the question now is how much water would be remaining in the pool after 4 hours. So after 4 hours, so what would be the amount of water? So that is what is required. But the difference this time is that the relation on the amount of water that is present at any instant of time is not exponential. But rather, it says here that the swimming pool drains at a rate, okay, proportional. Okay, so the rate of the draining, that is dV over dt is equal to the proportionality constant and then to the square root of the volume that remains. Okay, so the volume that remains, square root. Okay, so K times the square root of V. So as you can see on the given problem, so this time around, this is not an exponential decay, but rather, so the relation is given, so we have to solve the differential equation first, and that is using separable equation, that is dV over the square root of V, and that is equals to K dt. And then solving this one, so if our U would be V, and then, okay, so if U is V, so du would be dV. So thus, we could use the power formula. This is the same as V raised to negative 1/2 dV is equals to K dt. And thus, we'll have negative 1/2 plus 1, so we'll just have 1/2 over 1/2, or that would be V raised to 1/2 all over 1/2 is equals to KT plus C. And then, so this is the same as 1 over 1/2 is 2. So 2 the square root of V is equals to KT plus C. So this is our equation. So 2 the square root of V is equals to KT plus C. So if you want to make it exponential, it's fine. Okay. But we could just do it as is. So 2 the square root of V is equals to KT plus C. So let's now have our initial. So for us to determine the value of C, so that is when time is 0, V is equals to 375. So we'll have 2 the square root of 375 is equals to K times 0, so plus C. So therefore, so C is 2 the square root of 375. That is the same as 10 the square root of 15. So for our C. So we now have our new equation. 2 the square root of V is equals to KT plus 10 the square root of 15. And next, so we could use our next relation, that is after 1R. So what remains would be 300. So when T is equals to 1, V is 300. So 2 times the square root of 300 is equals to K. Then T is 1 plus 10 the square root of 15. So K then would be equal to 2 the square root of 300 minus 10 the square root of 15. So do we have, so 2 the square root of 300 minus 10 the square root minus 10 the square root of 15. So 2. So we have 20 the square root of 3 minus 10 the square root of 15. So that is for our K. And now that we have our K, so we could now have our final equation to be 2 the square root of V is equals to 20 the square root of 3 minus 10 the square root of 15. And everything is multiplied with T. So plus 10 the square root of 15. And now our, after 4 hours, so how much remains? So what is V? Okay, so what is V? So when time is equals to 4. So when T is equals to 4, so what is our V? So 2 the square root of V is equals to 20 the square root of 3 minus 10 the square root of 15, multiplied it with 4. So plus 10 the square root of 15. So 2 the square root of V then is equals to times 4 plus 10 square root of 15. That would be negative 80 the square root of 30, or 80 the square root of 3, and then minus 30. Minus 30 the square root of 15. And then divide it with 2. So we'll have the square root of V to be equivalent to 80, so 40 the square root of 3 minus 15 the square root of 15. So divide it with 2. And then taking the squares of both sides. So giving us to be or to have 125.16 kiloliters of water. Okay, so which remain after 4 hours. So 125.16. Okay, so that is the volume of the water that remains on the pool, okay, after 4 hours. Okay, so those are the examples. So for growth and decay, so we have 6 examples for that. So good day.